This is a video for AQA Further Pure Mathematics, Vectors Section 3.2, the equation of a plane in other forms.
We saw in previous videos that if we have a scalar product where we know that A dot B is equal to 0, then we also know that A and B are perpendicular to each other. And we can use this to define the equation of a plane, making use of a vector that is perpendicular to a plane. Now this may look a little bit unusual to begin with, but be assured that it does get quite easy once you get used to it. We can think of a plane then as having a unique direction which is perpendicular to the plane. So on this diagram here, n is our perpendicular or normal vector to the plane. So for any vector which is actually in the plane, then the normal is at right angles to that. So this any vector at all that we draw here, we have a right angle. So that means that the dot product of those two vectors must be equal to 0. So let's look at how we can use that idea to form the equation of a plane then. Here we've got a point A with position vector A and a general point P on the plane with vector R. So if the coordinates of P are x, y and z, then the vector R is just a vector x, y, z. If n is a normal to the plane, then from what we just said, the vector AP, which is in the plane, must be normal to that at right angles, and therefore we can say that the dot product AP dotted with n must be equal to 0. But we can calculate the vector AP as being the vector R minus A. So that's coming back along from R to A, and therefore AP is equal to R minus A. Now remember that R is just our vector x, y, z, and A is a known point, so that we know the values of the parts of the vector for A. So the equation of the plane then can be written as R minus A dotted with the normal vector is equal to 0. Or if we expand that, we can see therefore that R dot n minus A dot n is equal to 0, but A dot n is just some value P, so we can therefore say that the dot product R dot n is equal to some number P, where P is equal to the dot product A dot n. So in summary, we have that for a general point on the plane, which is given by the vector x, y, z, that the equation R minus A dot n will be equal to 0, gives us the plane. Remember that R is just a vector x, y, z. A is some known point, so we can write its vector like that. We're taking the dot product of that with a known vector for n, and that's equal to 0. That can be written as R dot n is equal to A dot n equal to P, where P is just the value of the scalar product of the known vector A with the normal. Let's look at some numerical examples of that. So this question, we've got a point A on the plane which is 1, 2, 0. So the position vector of A we can write in our diagram as 1, 2, 0. And the perpendicular vector 2, 5, 3. So 2, 5, 3. And first of all we need to work out the dot product of A and N to give us the value of P in our equation. So A dot N, the scalar product, is equal to 1, 2, 0, dotted with 2, 5, 3, which is 2 plus 10 plus 0, so 12. Therefore, R dot N equal to P gives us the equation x, y, z, or R, dotted with the normal 2, 5, 3 is equal to value of P, which is 12. And if we multiply out that dot product, we get 2x plus 5y plus 3z is equal to 12.
Well, in summary then, we have these ways of showing the equation of a plane. Firstly, the idea that we have R is A plus lambda B plus mu C, where we've got a point on the plane given by A and then two vectors B and C in the plane. Secondly, we could use the normal, so R dot N, where N is the normal to the plane, is equal to A dot N, or R dot N equals P, where obviously P then is equal to the dot product of A and N. And finally, Cartesian equation of the plane, AX plus BY plus CZ is equal to P. And here we've got that N, the normal, is the vector given by the coefficients of X, Y, and Z, so A, B, C. Note we can multiply the equation by any multiple other than 0 and it will represent exactly the same equation or exactly the same plane. To check your understanding of that then, you might want to pause the video and just consider these 6 different equations and decide which of them are parallel or which are indeed exactly the same plane. Well, for example, we can see that A and B have got direction vectors that are multiples of each other. So you can see from that one going to that one, we've actually just multiplied by 2. So these are going to be parallel. They're not the same value because we haven't multiplied the constant here by 2. If you look at D and F, the direction vectors are negative of each other. So this one here is negative 1, 1, 1, and this one here 1, negative 1, negative 1. You might also like to consider which of them are perpendicular. And perpendicular, of course, then we would need their direction vectors, the normals n1 dot n2, to be equal to 0. Well, that's the end of this video looking at equations of planes, and the next video we'll be looking at the angle between two planes.